Our topic today is ionic bonding. The question we're asking is, why do cations and anions combine to form new compounds? Our first idea is, what are the key players in our discussion? A key player is a cation. What's a cation? A positively charged particle. It's due to the imbalance of protons and electrons in an atom when an electron or electrons are given away. So cations are unstable in the sense that their outer shell has more electrons than needed or less electrons than needed. The goal is to find a situation in which the outer shell has a full number. Now that in most cases that's 8. The exception to that in our first 20 elements will be helium. Helium has 2 electrons in its outer shell. So we consider lithium in the periodic table atomic number 3 with 3 protons. As 3 protons attract 3 electrons, which are spinning around the outside of the positively charged nucleus. 2 of those electrons are tightly held in what we call the first shell. The third electron is further out and is not tightly held. In fact, lithium would rather not have that extra electron because that electron makes lithium unstable. So lithium will try to give away that electron as quickly as possible. Another example of an anion is a negatively charged particle, and this is also due to an imbalance of protons and electrons, only in a different way. So if we consider the anions, we would think of an outer shell that's almost full, an outer shell of electrons that if one electron or multiple electrons could be gained to make an octet to fill the outer shell, that would be desirable. Now, unlike cations, anions have a negative charge, and that is because if we count the protons, and we must remember that ions never lose their protons, the proton number will be different than the electron number. The electron number in this case would be greater than the proton number. Protons are positively charged, so we see here that the electrons would have these negative charges that exceed the positive charges for the protons. So overall, the ion itself comes up with a negative charge. So here's a picture that you can look at. We're looking at atoms that are seeking stability. So what is stability? An outer full shell. In this case, we talked about helium having 2 electrons for a full shell, and all the other elements in the first 20, their shell would be filled when there are 8 electrons in the outer shell. So in order to attain this status of having the outer shell full, it means that each one of these atoms is going to either choose to gain or lose electrons. So when an atom gains or loses an electron, remember that the proton number remains unchanged, but the number of electrons will either decrease or increase. You notice we have 2 electrons here tightly held close to the nucleus. So this is lithium, 1, 2, 3 electrons. Lithium would like to give this away. This atom over here has 2 electrons in the first shell, 1, 2, 3, 4, 5, 6, 7. So you can see that it has, at this point, it was in balance. But what happens is this electron from lithium is going to escape and will come over and join this atom's outer shell. So now that this outer shell will feel as though its configuration is full, as though it would be a noble gas. And so when lithium loses this 1 electron, it will also feel as though its outer shell is full. It would feel as though it were a noble gas. In this case, lithium will feel as though it's like helium. So why does this happen? When an element does not have a complete outer shell, it will either seek to gain or lose electrons if an ionic bond is going to happen. Once an ion forms, that means once an ion has either gained or lost electrons, there will be a charge, and that charge will attract ions that have the opposite charges. For example, a cation with a charge of +1 would be attracted to an anion with a charge of -1. Now, looking at the periodic table, we will learn that elements are ordered in groups. The arrangement of the groups are vertical. And we say that elements that belong to the same group, the same family, the same column, have similar configurations. That means the way that their electrons are organized in the shells surrounding this positively charged nucleus. And if an element belongs to a same group, it means that it'll have the same number of electrons in its outer shell. Here are two examples. We have the alkali metals found in family number 1 of the periodic table. And if we look at each one of these, their configuration would have 1 electron in the outermost shell. On the opposite side of the table, family number 17, we find the halogens. And the halogens are all very close to having completed an outer shell of electrons. Right next door to them on the periodic table, you find what's called the noble gases. The noble gases are inert. That means they're non-reactive. What we see is their outer shell has filled with electrons. So the halogens are so close to being in that same status. They just need one more electron. And so they will try to find that one electron. And when they find that one electron, halogens then will have a negative charge because there will be more electrons that are orbiting or surrounding the positive nucleus than there are protons with positive charge inside the nucleus. So what's the main idea? As we look at the periodic table, on the left-hand side, we see what are called the metals. Metals are elements that like to give away electrons. Here we see sodium with the atomic number 11. We consider sodium's atomic number, we think first shell fills with 2 electrons, second shell fills with 8 electrons, leaving 1 single electron in the valence shell. Valence shell is the outermost shell. Now this sodium atom is unlikely to remain in this state. Sodium is likely to form a cation. It will become positively charged and it will give away that 1 electron. It belongs to this group: lithium, hydrogen, sodium, potassium, rubidium, cesium, and francium. All of these will give away 1 electron. The next door family to this family, which is called the alkali metal family, is the alkaline earth family. We have beryllium, magnesium, calcium, strontium, barium, and radium. All of these would willingly give away not 1 electron, but 2, because each of the configurations for each of these elements would show us that the outermost, or the valence shell, would contain 2 electrons. So then we go to the opposite side of the periodic table. Here we find the nonmetals, and specifically we are looking for this group called the halogens. It would include fluorine, chlorine, bromine, iodine, and astatine. They will have a negative charge. Why? Because if you look at the configuration of fluorine, fluorine would have 2 electrons in its first shell and 7 electrons in its second shell. So it will take on 1 additional electron, giving it a negative charge, which would make it an anion. Here we see chlorine with an atomic number of 17, and we have to consider 17 positive charges would attract 17 negative charges. So we see 2 electrons in the first shell, 8 in the second shell, and then 7 in its outer or valence shell. 7 is so close to 8. So chlorine will seek some way to find 1 extra electron to make 18 electrons surrounding the 17 positive charges that are located in the nucleus of the atom. And when that happens, chlorine will become an ion. it would become a negatively charged ion, and we call this an anion. So over here, we have the alkaline metals and the alkaline earth metals who want to give away electrons. And over here, we have the halogens who would like to accept an electron. One of the things we need to consider at this time is what is happening between the ions. And we should remember that opposites attract. And particles that have the same charge, for example, positive and positive, will push away from each other. It's like you think of a magnet, the sides of a magnet or the ends of a magnet, positive and negative. The positive end of one magnet would push away the positive end of another magnet. However, the positive end of one magnet would attract the negative end of another magnet. An attractive force between positively charged cations and negatively charged anions will draw the atoms together, ultimately forming an ionic bond. And what we need to remember here is that in the process of forming this bond, energy will be required. And energy that we will find will be in the bonds. And eventually, if a bond is broken, then we will find that energy is released. Ionic compounds have no overall charge. Now, what do we mean by this? When a cation is attracted to an anion, say, for example, a +1 is attracted to a -1, and they merge to form a new thing, a compound. If I take +1 and -1 and add those together, the overall charge is 0. Now, sometimes we find metals that are attracted to what we call polyatomic ions. Polyatomic ions are numbers of atoms that group together, and in their group, they have a charge. So when we're thinking about this, sometimes in the periodic table, we see only elements that come together from the left and right-hand side of the table. But we also want to keep in mind that these elements on the left-hand side, the cations, can also merge with these polyatomic ions to form ionic compounds. Finally, newly formed compounds will have different properties than their components. Earlier, we looked at sodium. Sodium is a soft, gray, putty-like material, and it's highly reactive. And chlorine is a green gas. When we put the gray putty together with the green gas, we form something entirely new, something that you would like to put on your steak, or perhaps some other vegetable, or something else you eat to give it more flavor. Table salt. Table salt is an ionic compound. It's sodium combined with chlorine. The new properties are completely different. Sodium chloride is a white cube, a solid. It doesn't have the properties of either chlorine gas or sodium as a metal. So we form something new. Just remember, ions form compounds. They form ionic compounds. The elements that make up the compounds have become ions because the elements are seeking stability, and they will find the stability by gaining or losing electrons.